Hey learners, Jared here, and I have a confession to make. I am really attracted to Gravity Guy 2. Learners, swap out your batteries, get your calculators ready, because this is episode 2 of A.P.P. Physics. Now, Gravity Guy, along with a pretty sweet outfit, runs at a fairly constant x velocity of 3.2 meters per second, which for us Americans is about 8 miles per hour. Now, in the game Gravity Guy, you are spending the majority of your time in free fall, unless you activate these killer rocket boots that he has. Now, gravity in this game is around 12 meters per second squared, which is a tinge higher than our friendly Earth's gravity of 9.8 meters per second squared. Let's talk about Gravity Guy's rocket boots for just a second. Rockets work with a fairly straightforward concept. You eject material from beneath you, so you eject mass at a certain velocity. Now, because of the conservation of momentum, you eject mass with the velocity down, which is going to cause your mass a velocity up. Because in the initial stage of the rocket launch, you know, the really cool
10, 9, ignition sequence start.
5,
4,
3,
2,
1. Lift off.
Jing jing.
There was no initial momentum because the rocket was still attached to the platform. Then they release the platform and the rocket shoots off. So if there was no initial momentum, there can be no overall final momentum, which means whatever mass and velocity you're ejecting beneath you needs to equal the mass and velocity that you are having leave the Earth. Now, as you can see from the video, I activate Rocketman's boots at around this point. Now, that should change his X momentum, but it doesn't. It only changes his Y momentum, which is interesting because his boots are angled. So let's take this game one step further, and let's imagine that Gravity Guy is off of whatever planet he's on. He might not necessarily be on Earth because G is a little different, but I went ahead and made it a little homey for us. So here he is going around in a circular orbit with a constant speed v. Well, what would that speed have to be? It would depend on a couple of things. In order for something to be moving in a circle, you have to have a centripetal force. And for Gravity Guy, that centripetal force would be gravity on that guy. And the force due to gravity, the universal gravitation equation, would be capital G m1 m2 all over r squared, where G is our universe's gravitational constant, which who knows what it is in Gravity Guy's world. But m1 and m2 would be the mass of the planet and the mass of Gravity Guy, which alas we don't know. And then r would be the distance from the center of the planet out to the center of mass of Gravity Guy. Now, he's going around in a circle, which means our force due to gravity is our centripetal force, which is m AC for your centripetal acceleration. Now, m, well, when we think F equals ma, the m is what is doing the A-ing, what is accelerating. And in this case, Gravity Guy is the one going around in a circle. So he is the one that is accelerating, which means he is the mass that we plug in here. So if we make the planet m1, and I make gravity guy m2, I can set my gravitation equation equal to my centripetal force equation, which is just F equals ma. Now, centripetal acceleration is v squared over r. So I'm going to take Fg and Fc, and I'm going to set them equal to each other, but I'm going to substitute in v squared over r for AC. So I end up with g m1 m2 all over r squared, being equal to the mass of gravity guy, which we said was m2, times v squared over r. So one thing that his speed does not depend on is his mass. All that it depends on is the mass of what he is orbiting around and how far away he is. So take a look at this. If I multiply both sides by r to cancel this side and just get v squared, well, I would end up canceling that r. So I'd end up with the speed, v, is equal to the gravitational constant times the mass of the planet that he's orbiting around divided by r. So if r gets smaller, the closer you get to the planet that you are orbiting, the faster you need to go to maintain that orbit. The farther out you are, the less speed you need to keep yourself going around in a circle. For instance, satellites that have a geosynchronous orbit, like our cable television, well, actually not cable, satellite television, they stay over the same spot throughout the day. So their orbital period would be 1. Orbital period. V is 2 pi r over t. You could take 2 pi r over t and plug it in here and extrapolate even further.